In this lecture, I'll show the different steps to solve a numerical problem on Brayton cycle. I choose a very simple numerical. The numerical is in a gas turbine plant working on a Brayton cycle with a regenerator of 75% effectiveness. The air at the inlet to the compressor is at 0.1 megapascal and 30 degrees Celsius. The pressure ratio is 6 and the maximum temperature is 900 degrees Celsius. If the compressor efficiency and turbine efficiency is 80%, find the percentage increase in the cycle efficiency due to regeneration. Here already I have drawn the block diagram as well as TS, some part of the TS diagram. I will start before the compressor. Suppose this is the point 1. First of all, I will draw the simple Brayton cycle without regeneration. Suppose this is 1 point and this is 2 point. This is 2 point. This is not 2 point, basically this is 2s point. This is ideal Brayton cycle for. So 1 to 2s is reversible adiabatic compression process where we have to invest some work by WC. In TS diagram, this is 1 point and this is the reversible adiabatic compression. This is 2s. We have to invest some work in this section WC. Now after that the working fluid come to the turbine via combustion chamber where Q1 amount of heat will supply at constant pressure. That means isobaric heat addition. That means 2s to 3. So this is 2s to 3. Suppose this is the point 3. So here Q1 amount of heat will supply. And after that will passing through the turbine. This is the process that of reversible adiabatic expansion. So suppose this is 4s, point 4s. So in TS diagram that will straight vertical line. This is 4s. By the turbine we are getting some work WT. After that will come to the again compressor via condenser where some heat will reject. That means isobaric heat rejection by amount of Q2. That means this is the isobaric heat rejection in the condenser by amount of Q2. So this is the process. Here we are getting WT. So this is the ideal Brayton cycle without regeneration. When there will be compressor efficiency and turbine efficiency, definitely we have to consider the actual case. If this 1 to 2 process will be actual case instead of this ideal case, then the line will be just like that, because in actual case for compressor we required more work if we consider the ideal case with that. So this is 2. And for the turbine we get less amount of work from the turbine. So this is 4. So in compressor case 1 to 2s is ideal, that means reversible. 1 to 2 is what? Irreversible or actual case. For turbine 3 to 4s is ideal and 3 to 4 is actual expansion. Now this is the Brayton cycle without regeneration. Now if we install a regenerator between 2s and 3, that means between compressor and turbine, then there will be some heat addition to the working fluid after coming from the compressor by the exhaust gas from the turbine. Let's see what will be the block diagram. This is the block diagram. That means after 2s the working fluid condition will be suppose 6, and after 4s the working fluid condition will be suppose 5. In TS diagram what will be 6? This is the point 6 and this is the point 5. This is the point 5. Is that clear? Now, what is the given data? The given data is effectiveness of the regenerator. The effectiveness of the regenerator is what? That is equal to T6 minus T2 divided by T4 minus T2, because whenever there will be compression efficiency as well as turbine efficiency, then we have to consider only actual case. That means actual cycle in TS diagram is 1, 2, 3, 4, 1, and along with the regenerator, that means 6 and 5. So effectiveness is T6 minus T2 divided by T4 minus T2. The initial temperature, that effectiveness is how much? 75%. That means 0.75. 0.75. And temperature T1, that means before entering into the compressor, the temperature is how much? T1 is 30 degree Celsius. That should be converted in Kelvin. So in Kelvin, this is T1. Similarly, the T2. T3 is equal to how much? 900 degree Celsius. That will be converted into the Kelvin. And compressor efficiency as well as turbine efficiencies, that means efficiency of compressor as well as efficiency of turbine is equal to how much? 80%. That means 0.8. Is that clear? Now, pressure ratio. Pressure ratio is what? Pressure ratio RP is equal to what? P2 by P1. Though we know that this cycle working between two pressure line. One is condenser pressure, another is combustion chamber pressure. So, pressure ratio definitely P2 by P1, that is also equal to P3 by P4. P3 by P4, that is equal to how much? That is equal to 6. Pressure ratio is 6. Now, start the numerical. First of all, without regenerator. Without regenerator. Now, this 1 to 2s is reversible process, and also 3 to 4 is also reversible process. For these two cases, we can write T2s by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma, that is also equal to what? T3 by T4s. T4s, that is equal to what? This P2 by P1 is pressure ratio, which is equal to P3 by P4. So Rp to the power gamma minus 1 by gamma. From this relation, that is equal to, though we know this Rp value, that is 6 to the power gamma minus 1 by gamma. So from this relation we can get T2s value as well as T4s value. Okay, now consider the compressor efficiency. From the compressor efficiency of compressor is how much? 0.8. That is equal to, for the compressor case, in ideal case we record less work, for actual case we required more work. So ideal work required, that means that will be T2s minus T1 divided by T2 minus T1. From that relation we can find out T2 minus T1 value as well as T2 value. Okay, we required this value for next step. Similarly, from the efficiency of turbine, that is also 0.8. For the turbine case, we have the less work in actual case if we compare with the ideal case. So for that case, actual work output, that means T3 minus T4 divided by T3 minus T4 divided by what will be T3 minus T4s. From that relation we can get T3 minus T4 value also T3 value is already known, T4 value of T4. Now for the turbine work, so WT is equal to nothing but, we have to get the actual value. WT is nothing but mass flow rate into H3 minus H4, that is equal to MCP into T3 minus T4 kilowatt, because this is in Kelvin, kilojoule per kg Kelvin, that is kg per second, so kilowatt. And similarly W compressor will be mass flow rate into H2 minus H1, that is equal to mass flow rate into Cp T2 minus T1 in kilowatt. This T2 minus T3 and T3 minus T4 and T2 minus T1 value we can get from this equation and this equation. Is that clear? And now we have to find out the heat supply Q1, which has been supplied between 2 to 3 for without regeneration. So Q1 is equal to mass flow rate into H3 minus H2, that is equal to also mass flow rate into Cp into T3 minus T2 kilowatt. So efficiency of the cycle without regeneration is equal to, what will be? Without regeneration will be W net divided by Q supply, that is Q1. W net is WT minus WC divided by Q1. So we can get the value of this efficiency without regeneration for that case. Now with regeneration. So now with regeneration case. With regeneration case, what happened? After compression, the working fluid heating up by the combustion, by the exhaust gas from the turbine in the regenerator. So heat supply has been taken place only between what? 6 to 3, because this amount of heat will supplied by the heat which has been carried out by the exhaust gas. So only heat has been supplied outside the system is only between 6 to 3. So with regeneration, heat supply Q1 will be what? Definitely mass flow rate into H3 minus H6. Now we have to find out this H6, because H6 till now is unknown to us. So for this H6 we required this relation, that means effectiveness of the regenerator. So effectiveness of the regenerator is how much? 0.75 is equal to T6 minus T2 divided by T4 minus T2, that is equal to 0.75, where except T6 all are known. So from there we can get the T6 value very easily. By the T6 value, if we put here, then we can get the Q1 with regeneration. So after getting Q1 with regeneration, we can get the efficiency of the cycle with regeneration, that is W net divided by Q1 with regeneration. Though the W net remains same, because there is no change of this turbine work as well as compressor work. So that will be the efficiency. So we can get the value of that by putting the value Q1 with regeneration and W net, which has been evaluated earlier. Where? This one. So this is the efficiency of the cycle with regeneration. Now what is the percentage? The percentage of efficiency increase, that will be equal to how much? Efficiency with regeneration minus efficiency without regeneration divided by what? Divided by efficiency without regeneration into 100%. So this is the final answer. So I hope it will help you to understand how to solve a numerical with simple relation among pressure, volume and temperature and heat supply or heat rejection relation. So thank you.